You know, if you ask pretty much anyone in charge of anything, a CEO, a city planner, a programmer, what the goal is, you're gonna get the same answer: efficiency. We are obsessed with optimization. It's kind of like the religion of our modern world, right? We want to do more with less, make things faster, cheaper, leaner. Okay, let's really get into this, because what if that core belief is just fundamentally wrong?
This quote, it just nails the whole problem perfectly. When you optimize a system to get rid of every single ounce of fat, every last second of delay, you're not just making it better, you're also making it incredibly brittle. You're basically trading your ability to handle a surprise for just a little bit more speed.
I mean, a car with no spare tire is amazing, on a perfectly smooth, predictable racetrack. But our world, it isn't a smooth track. Just look at this graph. The number of natural disasters has shot up like crazy since the 1960s. So the road we're on is getting a whole lot bumpier. But all our systems are still designed like we're on a perfect raceway.
And that brings us right to the heart of what we're talking about today: the efficiency paradox. This relentless, almost single-minded chase for optimization is actually building systems with these hidden, catastrophic weaknesses. And believe it or not, this is not a new problem. In fact, the first time this obsession with efficiency broke the world was over 3,000 years ago.
So picture this. Around 1200 BC, the world was surprisingly connected, a lot like ours is today. But its entire economy, all its military power, was built on bronze. And to make bronze, you need tin. That tin came from one place through one hyper-efficient but very, very long supply chain. So when a few small things went wrong, nothing major, just some droughts and migrations, that chain didn't just bend, it shattered. No tin meant no bronze. And just like that, entire civilizations just collapsed. They'd optimized everything for growth, but had zero room, zero buffer for a little bit of chaos.
So what's the trade-off we're making here? Well, think of it like this. A Formula One car is the absolute pinnacle of efficiency. It's a work of art, an engineering marvel. But it's designed for a perfect world. A single pothole can literally destroy it. A tank, on the other hand, it's wildly inefficient. It's slow, it guzzles fuel like there's no tomorrow. But it is resilient, it can drive straight through a brick wall. The problem is, our modern world is full of engineers building F1 cars, when what we might really need are a few more tanks.
Okay, so if our own logic keeps leading us to these fragile systems, where do we even look for a better model? What if the answer has been staring us in the face for millions of years? Because, as it turns out, nature has already solved this problem.
Take a look at these two images. On the left, you've got a power grid that we built. On the right, you have a natural food web. If you really think about it, they're the same thing at their core. They're both networks that move energy around. The huge difference is that ecosystems have this built-in ability to survive shocks. So, a bunch of researchers started asking a pretty cool question. Could we learn from their design?
And this question gave birth to a whole field called ecological network analysis, or ENA for short. It's basically a toolkit for reverse engineering nature's blueprints. The whole point is to figure out, with actual numbers, how ecosystems pull off this amazing balancing act between being efficient enough to grow and resilient enough to survive.
So, ENA boils this whole thing down to two key ideas. First, you have ascendancy. Just think of that as efficiency. It's how streamlined and organized the network is, like one giant power line going straight from the power plant to your city. Then you have overhead. That's your resilience. It represents all the extra, flexible pathways in the system, all the backup options for when something goes wrong. This is like having lots of smaller power lines and backup generators. Sure, it seems more wasteful on a good day, but it's a lifesaver on a bad one.
And this right here is the absolute key. Nature doesn't try to max out efficiency, and it doesn't try to max out redundancy either. Instead, every healthy, sustainable ecosystem operates within this very specific sweet spot, a perfect balance between the two that scientists call the window of vitality. If you're too efficient, you're brittle. If you're too redundant, you're stagnant. All the magic happens right there in the middle.
This is all really fascinating stuff, but can we actually do anything with it? Can we take this blueprint from nature and apply it to our own critical systems? Well, some researchers decided to give it a shot, and they focused on one of our most important systems, the electrical power grid. So using these ENA tools, they analyzed a standard model of a power grid. And what they found, well, that green square you see there, that's the grid. It's way over on the right. That means it has a super high degree of order. In other words, it's very efficient. But look, it's nowhere near that healthy window of vitality. By nature standards, our grid is dangerously fragile.
So that led them to the big question, the core of their research. Could they actually use an algorithm, not to push for more raw efficiency, but to push for what they called ecological fitness? To put it simply, could they redesign the network of power lines to deliberately move it into that healthy, balanced window?
And so they did it. They ran the models and they let the algorithm reroute connections and add new ones, all with the goal of hitting that perfect ecological balance between efficiency and resilience. And the results? They were pretty remarkable.
Just look at this. This is the after picture. By adding intelligent redundancy, not just random parts, but smart connections, the new ENA-inspired grid design now sits right in the middle of the window of vitality. It's not a hyper-optimized F1 car anymore, it's something much, much more robust. But the big question remains, does that balanced design actually perform better when things go wrong? To find out, they basically tried to break both designs. They ran all these simulations where 1 or 2 or even 3 parts of the grid failed all at the same time. The result? It wasn't even close. The NA-inspired grid, the one that's balanced like a healthy ecosystem, had way fewer overloads and blackouts in every single scenario. It was, without a doubt, more resilient. Okay, so let's pull the lens back out to the bigger picture. We've seen that the design inspired by nature can make our power grids a lot stronger. But what does this mean for how we think about, well, building everything else?
Now, you might be thinking, okay, I get it. So the answer is just to add more of everything? More power lines, more warehouses, more spare parts? Is the solution just brute force redundancy?
And the research is really clear about this. No, absolutely not. The ENA-inspired solution wasn't just about randomly adding more connections. It was about adding the right connections in the right places to build a smarter, more robust overall structure. It's about intelligent design, not just having more stuff.
And this forces you to completely rethink what we call waste. That extra capacity, those backup pathways, that warehouse full of spare parts that a just-in-time manufacturing consultant would scream about, yeah, it all looks like a failure of planning on a quarterly report. But if you zoom out and look at a long enough timeline, that isn't waste. That's insurance. That's survival.
So really, the whole point is this. From our supply chains to our financial markets to our power grids, we have engineered a world that is breathtakingly optimized for a perfect best-case scenario day. The question this research really leaves us with is a tough one. Are we willing to pay the price to survive the worst?